Professor Tsung-En from Department of Microelectronics. This is the course of Semiconductor Device Physics opened in 2024 fall. Here is some administrative details. It is an English taught course, but you can interact with me in Chinese if you have any questions. And it is a 3 units course. And the textbook detail will be explained in the next slide. And my office hour is held in every Tuesday 10 to 11:30 or by appointment. Here are the reference books that I will use in this course. I divide my course in chapter 1 and 2. In the chapter 1, I will mainly focus on the semiconductor physics, and that will be explained based on Neiman's textbook more. In the chapter 2, I will focus more on the device physics. So in that part, I will refer to Professor Chen Minghu's textbook and also Streetman's textbook. And the other 2 textbooks are academian Professor C and Professor Yuan Tao's textbook. That will be more advanced, but you can take it also as a further reference. Let me briefly introduce myself. I was graduate from National Jiao Tong University in 2014 in the Department of Electronic Engineering. After that, I received my master and doctorate degree from the University of Tokyo in Japan. About my professional experience, before coming to NYCU as a professor, I have been as a principal engineer in the TSMC, which is in the Department of the Corporate Research, which is a research team in TSMC, about 3 years. And my research background is mainly focused on the thin film transistor, including oxide and the semiconductor and the 2D materials channels. And the other part is the memory device, focused on the ferroelectric non-volatile memories. And furthermore, I would like to introduce that I'm interested in about the 3D integration of those transistors and memories on the advanced CMOS technologies. About the grading of this course, 20% will be the homework, and I will divide them into 6 sets. And about the exam, I have 2 exams. One is a midterm exam. The other one is a final exam, which will count about 35% each for each exam. And the last part is a 10% for the class participation. I won't check all the students every class, but I will try to have some Q&A randomly in the course, and that would be the way how I check whether you participate or not. And the most important is every homework or exam cheating is strictly prohibited. About some suggestions for learning this course. To understand the physics behind this in these lessons, please try to draw the figure by yourself and try to, with some imagination, and try to understand the way how I explain those graphs, and try to translate into your words to explain those figures. And the other suggestion is try to prepare a net notebook and derive those formula in the textbook in your notebook by yourself, and that will help you to understand and to be more familiar with those formula and the physics behind it. Okay, here is the outline of this course. Since this is the undergraduate course, so I will focus more on the concept more than some mathematical derivation. In chapter 0, it is like an introduction of this course, so it is very brief. And chapter 1, as I mentioned, I will mainly focus, the topic will mainly focus on semiconductor physics. And I divide them into 4 sub-chapters. In 1.1, I will introduce the quantum theory of the solid. In chapter 1.2, let's discuss about the electrons and holes at the equilibrium situation. In chapter 1.3, we will introduce about the carrier transport phenomena, including the drift and the diffusion. In chapter 1.4, we will shift from equilibrium condition to non-equilibrium condition, which is mainly attributed to the excess carriers situations. In chapter 2, based on the learning from the chapter 1, we will extend to the device physics more. And we won't discuss BJT in this course. We will only focus on the MOSFET, which is the mainstream in our current technologies. As a MOSFET, we can divide them into the PN junction, metal semiconductor contact, which will be discussed in chapter 2.1, and all the other part is the MOS capacitor, which we will discuss in the chapter 2.2. And the last part, we will integrate the learning from 2.1 and 2.2 to 2.3, which is the MOSFET, and which that is you already may have already familiar with it when you learn the electronics 1 and 2. Okay, let's move on to the chapter 0. The most important of the objective of this course is to inspire your interest in the solid state electronics. So hopefully I hope that you will enjoy this class and learn some interest part in the solid state electronics in any way, and that can help your further learning or research in the future. The introduction, I would like to start about AI, which is the most hot topic in recent trend. We all know that AlphaGo or even the ChatGPT becomes a very powerful machine to change the world, the way we work. But have you think about how they booms? Why they booms after in these 5 years, not in the 1990 days at that time? That is all about. The answer is all about the semiconductors technologies. Without the powerful semiconductors energy efficient device with high density logic or memories, with advanced technology or advanced packaging, AI can boom. So if we want to further drive the computing efficiency in the AI chips, no matter it's GPU or high bandwidth memory, we need to understand the fundamental how to advance the semiconductor in no matter it's CMOS or packaging or any kind of emerging memories. Because moving forward to the most advanced one, let's return to very, very fundamental or the history of the transistor. Transistor is invented even in 1900, which is we call it that time is a vacuum tube, but that is the concept already have the switching matrix in this device. And after the advance, the most important is the transistor is invented, field effect transistor invented in 1926, and at that time it's a 3-terminal device, and which we use mainly in the current technology is MOSFET, which is invented in the 1959 in the Bell Labs. And after 4 years, complementary MOSFET is invented by Professor Shah, which the inverter is consists of one MOSFET and one P MOSFET. Although that is invented in very long time ago, but finally it is become the mainstream products in around close to 2000. And after that, Dr. Dinner from IBM uh, introduced a way that is beyond the Moore's law. Is called Dinner scaling, which explains how the dimension scales with the scaling of the power, the area, and the performance. And you will think about it. Okay, the Dinner scaling. When is the end? So that is the main topic. What my current interest, what my current research are interested in, and that is also your opportunities if you are also interested in it. But for this course, we will try to start from very basic part, from the unit of the MOSFET. You need to understand the most fundamental physics first, then you can have some breakthroughs for this modern or next generation energy efficient device for the future. So for this graph, I'm not going to explain all the details, but I would like to let you know for current advanced chips, we need to collaborate or integrate with many aspects, not only device, but also with the circuit design, the system design, and also from the very bottom, from the material exploration or some invention. And if we want, and also we want to make our device very small for high density transistor memory. So we need very high resolution lithography. So integrate those stuff, or try to find your opportunity in this industry is interesting, and you have many opportunities. So try to explore what you are interested in the future. So as I mentioned, just use one graph to let you know why I would like to introduce more about MOSFET rather than BJT in this course, because after 2000 years, MOSFET has dominated almost 90%, and it is keep increasing to almost more than 90%. Rather than using a very mathematical way or physical way to explain the MOSFET, let's use gossip to understand that how we can to imagine what is a transistor. When we tight our valve closed, then the transistor can be turned off. But when we open it, then the transistor will like a current water flow in we can turn on it like a conductor. And when we switch off it, it will become like a resistor. So that is the way we imagine as the switching. And that is the equivalent circuit of the MOSFET, which is consists of the capacitor in the insulator and the capacitor in the channel. And the surface potential of this channel can be explained by this formula. You can understand this graph now, but I believe you will understand after you finish all the course. And what is the aim for design efficient energy efficient CMOS? It's all about the power reduction. You can see the total power consumption is determined by the power we use in the power with the power VDD means the applied voltage we used, and that determined by the how we operate our device, and what is the standby power, and also the leak, and all of these terms are a function of the applied voltage. So reduction of the supply voltage is critical for low power CMOS. So how to reduce the VDD? This is an example of the IDBG curve. If you want to reach the same on-state current, and with a lower VDD, there are several ways. First, we can try to improve the on-state current by higher channel mobility, and this formula will also explain in chapter 2. And the other way is to improve the slope of this switching behavior, which is mainly determined by the trap or substructure leakage or short channel effects such as BIBO. And the way to improve that part can be summarized as the channel thickness thinning, or equivalent oxide thickness thinning, or trap density reduction. And the last part is the leakage at the 0 volt of gate bias. We can reduce this part by tuning the VT, such as carrier concentration modulation, and also the same, the body thinning. So hopefully, if you can understand the device fixation in this course, then you can design the way to further improve the VDD in your device. So I will skip this part, but that just give you the way how this thin body channel can works, or how we can imagine it in the gaussian. Okay. So the introduction in the course, that is the last part. In the core of this chapter 1, we will introduce the quantum theory in the solids, right? So you may have learned the quantum well, no matter is finite or infinite potential well in the modern physics, which is have been taught in second year of your course. And we will try to explain that what will happen when this potential well becomes closer and becomes arranged as a periodic way. And after that, how does the band diagram form, and why we use energy and K-vector way to EK diagram to explain the solids properties. And with this band diagram in the EX diagram, how can what is the Fermi level, and how to extract the carrier concentration in the band diagram? What is the density of state, and so on. And finally is the transport with the diffusion and the drift, and also the NP type hole, and what is hole, what is electron. That is the main transport way. And the other part is from the continuity equation, how to understand the generation and the recombination rate if we have an excess carrier. And the core of this course in the chapter 2 is we want to understand the MOSFET from the learning in the chapter 1. So as I mentioned, I divide them into 3 parts. First part is the PN junction inside the MOSFET. So we need to start from what is PN junction, and what is the state at the equivalent or the forward bias and the reverse bias. And the second part is we further transform from PN junction to MS junction, and we can also call this Schottky diode. As a metal semiconductor contact, the band diagram will form a Schottky barrier layer. So how to determine the barrier height and how to reduce it or modulate it, you can learn from this part. And the third part is the gate of this MOSFET, which is mainly determined by the behavior of the MOS capacitor, metal oxide semiconductor, In the Venn diagram, you can see that when we apply a bias, there are many regions of the semiconductor from accumulation, flabellum, depletion, in threshold voltage. After threshold, you can become the inversion, strong inversion, and weak inversion, and the strong inversion. And we can derive the electric field and the potential well from the Poisson equation. And finally, if we can consider these three terms, then we can totally fully understand what a long channel MOSFET can be operated. So this is my teaching proposal for the Department of Microelectronics, which is a newly established department in NYCU from 2024. I hope that our students can learn the device physics, experiment, characterization, and also modeling with a more comprehensive way. And based on this learning, you can extend the current technology with the industrial collaboration, no matter it's away from the research collaboration or from intern, or even try to interact with the lecture from industry. So that is some of the suggested course that you can take after learning our semiconductor device physics in this course.